Good morning, cadets. Now, before we proceed further, we'll learn about molar specific heat. In the previous session, we have discussed about specific heat and heat capacity when the substance is measured in units of mass, that is in terms of kilogram. If the amount of substance is taken in mole, SI unit of amount of substance is mole. So if the amount of substance is taken in mole, then we term it as molar specific heat. So we define molar specific heat as amount of heat absorbed or given off to change the temperature of a mole of a substance by 1 degree Celsius or by 1 Kelvin. Amount of heat absorbed or given off when a mole of substance changes its temperature by 1 Kelvin is called as molar specific heat. Amount of heat absorbed or given off. Given off means released. When a mole of substance changes its temperature by unit value. Changes temperature by unit value means either by 1 degree Celsius or 1 Kelvin is called as molar specific heat. Now, for gases, there are two types of molar specific heats. For a given mole of gas, if the temperature changes or heat is given off or heat absorbed at constant pressure, keeping constant pressure, then that is called as molar specific heat at constant pressure. So there are two types, Cp and Cv. Cp is molar specific heat at constant pressure. Keeping constant pressure level, it is called as Cp. That is molar specific heat at constant pressure. Same definition. Amount of heat absorbed or given off when a mole of substance changes its temperature by unit value at constant temperature is called as molar specific heat at constant pressure. Once again, amount of heat absorbed or given off when a mole of substance changes its temperature by unit value at constant pressure, keeping pressure constant, is called as molar specific heat at constant pressure. Similarly, if volume is kept constant, if pressure varies by changing temperature and volume constant, by changing temperature and keeping volume constant, then it is called as molar specific heat at constant volume. Molar specific heat at constant volume. So again, same definition. Amount of heat absorbed or given off when a mole of substance changes its temperature by 1 Kelvin or 1 degree Celsius, keeping volume constant, is called as molar specific heat at constant volume. So later on, we are going to relate this relation between Cp and Cv. This is for molar specific heats at constant volume and constant pressure. So the equation for molar specific is delta Q by mu delta T. Delta Q by mu into delta T, where mu is number of moles of a substance. Number of moles of substance. Substance taken in that mu number of moles. It is called as molar specific heat. Therefore, we got two values. Just to take some examples, if you consider the examples of nitrogen and oxygen. Molar specific heats of nitrogen. And oxygen. First I am writing Cp. Molar specific heat at constant pressure. It is 29.1 joule per mole per Kelvin. Joule per mole per Kelvin. Cv value for nitrogen. Cv value for nitrogen is 21.1 joule per mole per Kelvin. This is of nitrogen. One more example is oxygen. Cp value of oxygen is, from the data I am writing, 29.4 joule per mole per Kelvin. Cv value 21.1. This is 21.8. 21.1 and this is 20.8. 20.8. So there is a relation between them. You can see, if you take the difference between Cp minus Cv, there is a constant. 21.1 minus 20.8, it becomes 8.3. 8.3. 29.4 minus 21.1, again it is going to be 8.3. So we are getting Cp minus Cv for a mole of substance, mole of gas like this. It is a fixed value, 8.3 joule per mole per Kelvin. This is nothing but universal gas constant. So we get the difference between molar specific heats. Cp minus Cv is always constant. So in the later discussions we are going to derive this relation how Cp minus Cv for gases is going to be a fixed value, that is universal gas constant 8.3 joule per mole per Kelvin. Mole per Kelvin. And SI unit of molar specific heat. SI unit is, as I have written already, joule per mole per Kelvin, because amount of substance is taken in moles, therefore it is in joule per mole per Kelvin. So like that, if you take any other example, the ratio is always fixed. For helium, for example, helium, if you take helium, 1 mole of helium, Cp corresponds to 20.8. Cv corresponds to 12.5. Again, if you take difference, 20.8 minus 12.5, it is going to be 8.3. Cp minus Cv is going to be 8.3 joule per mole per Kelvin. So these are the examples. 1 mole of gases. Okay. Now we are going to learn more about it later on. Now before we go further, we are now learning calorimetry. As I stated earlier, calorimetry is again branch of physics, which basically branch of thermodynamics, which deals with study of measurement of heat. Metry means regarding measurement. Calorie means unit of heat. How heat can be measured, that is called as calorimetry. So calorimetry means measurement of heat. First we shall understand what is the meaning of isolated system. Isolated thermodynamic system means the one which is having a fixed value of heat, isolated from the surroundings, which does not change its heat with the surrounding. It will be having fixed value of temperature. That is called as isolated system. Isolated system or isolated thermodynamic system is the one which does not exchange the heat. It will neither give out the heat nor absorb the heat. Such a system is called as isolated system. The thermodynamic system which neither releases heat or absorbs, neither releases heat nor absorbs heat from the surrounding. From the surrounding is called as isolated system. There may be an isolated system in which different parts of the isolated system may be having different temperatures. Think of one isolated system which is not exchanging the heat to the surrounding. But in one particular isolated system, there may be different parts which will be having different temperature. Then there is a exchange of heat between those different parts. A part which is at higher temperature will be able to release the heat to a part which is at lower temperature. So heat is supplied from a part at a higher temperature to a part at lower temperature until the equilibrium is attained. Heat is transferred from a part at a higher temperature to a part at lower temperature until both of these parts attain common similar temperature, and that state is called as equilibrium state or steady state, thermodynamic equilibrium state or steady state. Steady state is the one at which the temperature of both the systems is same. Such a state is called as steady state. Until steady state is attained, there is exchange of heat. In an isolated system, if there are different parts at different temperatures, then heat is lost by a system or by a part. Heat is lost by a part at higher temperature to a part at lower temperature until steady state is attained. Until steady state is attained. Steady state is state at which both will have same temperature. Steady state is the one at which both will have common temperature. So that is what we call as steady state. So using this, we term principle of calorimetry. Principle of calorimetry is the one in which we state that in equilibrium, in steady state, heat lost by a system at higher temperature is equal to heat gained by a system at lower temperature. So this is called as principle of calorimetry. So in general, we can say a very important principle of calorimetry that when a body at higher temperature is in broad contact with a body at lower temperature, then heat lost by body at higher temperature is equal to heat gained by body at lower temperature until steady state is attained. So this is called principle of calorimetry. So when a body at higher temperature is brought in contact with a body at lower temperature, then there is exchange of heat. Heat lost by a hot body. That is, body at higher temperature is equal to heat gained by the body at lower temperature. So heat lost by hotter body is equal to heat gained by colder body. This is called as principle of calorimetry. This is the principle which is attained, which is stated in steady state. At steady state, until both of them attain common temperature. This is called principle of calorimetry. This is possible when no heat is lost to the surroundings. The entire body at higher temperature is supplying heat to the body at lower temperature. There is no loss. If there is no loss of heat to the common surrounding system, then entire heat lost by the hot body is equal to entire heat gained by body at lower temperature or body at yes, the body which is colder. Body at higher temperature will be giving out the heat. Body at lower temperature is absorbing the heat. So heat lost by hot body is equal to heat gained by cold body. This you will understand by solving a problem. This you will be able to follow when we just solve one simple problem. Just know that we will be able to understand what is calorimetry. So calorimetry involves a device which is used to measure heat. A device used to measure heat is called calorimeter. Calorimeter is a copper beaker. It's a copper container, copper beaker or copper container which is having a closed lid, a lid with a stirrer. It is provided with a insulator lid with a stirrer, and stirrer is going to pass through this. This is copper stirrer, and here there are two holes. Right? There are two holes. One hole is meant for passing the thermometer, and another hole is meant for passing the stirrer. So this is insulator lid, wooden lid, you can say, wooden lid, and here it is copper vessel or copper beaker, and this is copper stirrer. And inside it will be filled with water, and this is surrounded with a wooden jacket or a jacket which is insulating the entire system, insulator jacket, like it will be covered with glass wool or thermocol, so that it is glass wool or thermocol, so that it is totally isolated and insulated. So this is insulation using glass wool or thermocol. And this entire system is again taken in a wooden jacket. Again this is kept in a wooden jacket, wooden box. Completely it is covered with wooden box. So that it is totally isolated. Wooden case or box. So the entire copper vessel which is filled with water and copper vessel closed with this insulation lid will not be exchanging heat to the surrounding. Okay, this is what we call as calorimeter. Calorimeter consists of a copper beaker with a copper stirrer provided with a thermometer. Thermometer provision is there, and it is closed with a wooden lid, and this entire calorimeter is kept in, it is surrounded with the insulation jacket using the thermocol or glass wool. This is insulation jacket, and this is entirely taken in a wooden box or wooden case, so that heat is not lost to the surroundings. So this system provides us to measure heat, and the device which is used to measure heat is called as calorimeter. So let us see one example how calorimeter is helpful in the measurement of heat and in the measurement of specific heat. Okay. Yes, now look at the problem. A sphere of 0.047 kg aluminium at 100 degrees Celsius temperature is taken into 0.14 kg calorimeter. A sphere is taken inside whose mass is 0.047 kg. Aluminium sphere at 100 degrees Celsius. Its temperature is 100 degrees Celsius. This is taken into 0.14 copper calorimeter. This is the copper calorimeter, 0.14 kg mass. It is containing 0.25 kg of water. This is containing 250 gram of water at 20 degrees Celsius. Aluminium sphere is hot. It is at 100 degrees Celsius. It is taken into water at 20 degrees Celsius, taken in a calorimeter, copper beaker. So temperature of copper beaker and temperature of water is same before taking the aluminium sphere. Now once we take the aluminium sphere at 100 degrees Celsius into the water, then when the lid is closed and kept inside the woolen jacket, when no heat is lost to the surrounding, then at steady state, heat lost by the hot sphere is equal to heat gained by water and the copper calorimeter. Next, the temperature of water rises and attains a steady state of 23 degrees Celsius. It attains a steady temperature of 23 degrees Celsius. You are asked to calculate the specific heat of aluminium sphere. What is the specific heat of aluminium? Specific heat of water is known. 4.18 into 10 raised to 3 kg joule per kg per Kelvin. Specific heat of copper is 0.386 joule per kg per Kelvin. With this data, you are asked to calculate what is the specific heat of aluminium. Okay. At steady state, heat lost by aluminium sphere at 100 degrees Celsius is equal to heat gained by, there are two things which are giving the heat here. One is water and another is calorimeter. Heat gained by water and copper calorimeter, both at temperature 20 degrees Celsius. So first we will calculate what is heat lost by the aluminium sphere. So first I will write mass of aluminium sphere. We take it as M1. M1 is equal to 0.047 kg. Then specific heat we don't know. Let specific heat of aluminium be equal to S. Let it be S. Let us take it as S. Then change of heat. To calculate change of heat, we should know what is final temperature. Final temperature is, let us say it as T. T equal to 23 degrees Celsius. This is given here, 23 degrees Celsius. Initial temperature of aluminum sphere T1 100 degrees Celsius. So from 100 degrees Celsius it is attaining finally 23 degrees Celsius. So we can calculate what is delta T. Therefore delta T equal change of temperature delta T1 equal to T minus T1, that's equal to 100 minus 23, that is 77 degrees Celsius. This is the data for calculating heat loss by the aluminum. Therefore I can write the equation for heat loss by aluminum. Aluminum sphere is equal to mass into specific heat. Mass is M1, specific heat is S into delta T1. Delta T1. So this I can write as mass M1. M1 is 0.047 into specific heat. We don't know. Delta T is 77 degrees Celsius. So for this equation 1. In the same way, we can calculate what is heat gained by water and heat gained by copper separately, and then we can add together. So first we will calculate heat gained by water is equal to, let us take it as mass of water as M2. M2 into specific heat of water as S2 into change in temperature. So there is going to be increase in temperature now. So increase in temperature is calculated as, okay, here I have made an error. Here it is T1 minus, T1 is the initial temperature and T is the final temperature. Yes, T1 minus, here change in temperature is going to be T minus T2. T minus T2, where T2 is the initial temperature, 20 degrees Celsius. So I can write it as here T2 equal to 20 degrees Celsius and T equal to 23 degrees Celsius. These are given, and mass of water is given, that is 250 gram. Therefore I can write it as 0.25 kg into 4.18 into 10 raised to 3, that is specific heat of water, into 23, that is final temperature, minus initial temperature of water, 23 minus 20, that becomes 3 degrees Celsius. So this is how we write heat gained by water. So heat gained by water, so you can call it as second. Similarly, heat gained by copper calorimeter. Heat gained by copper calorimeter. So here thermometer is helping you to read this final temperature. The final temperature is 23 degrees Celsius at steady state. Okay. Heat gained by copper calorimeter can be again calculated as M3, where M3 represents mass of copper calorimeter. M3 into S3, specific heat of copper, into change in temperature again, T minus T2. This is also having the same temperature, that's of water, 23 minus 22. So mass of copper is given, mass of copper is 0.14 kg, 1/4 into specific heat 0.386 into 10 raised to 3 into 23 minus 20 again. So call this equation number 3. So equation at steady state, we apply this principle of calorimetry. Heat loss by aluminum is given by equation number 1 equal to heat gained by water and copper. Heat gained by water and copper calorimetry is given by equation number 2 plus equation number 3. So equation number 1 is equal to equation number 2 plus equation number 3. That helps us to calculate specific heat of aluminium. Okay, I will write on the other side. Using principle of calorimetry, we can write at steady state, heat lost by aluminum sphere is equal to heat gained by water plus calorimeter. So equation number 1 must be equal to equation number 2 plus equation number 3. So equation number 1 we have 0.047 into S into 77 is equal to this one 0.25 into 4.18 into 10 raised to 3. 23 minus 20 is 3 plus equation number 3 0.14 into 0.396 into 10 raised to 3. Again 23 minus 20 is 3. So 10 raised to 3 into 3 is common. So this becomes, after calculation, if you take out 0.25 into 4.18 plus 0.14 into 0.396 into 3 into 10 raised to 3 as common, then this helps you to go for simplification. 0.047 into S into 77. Therefore, the specific heat of aluminium S is equal to, so if you simplify this entire thing, 0.25 into 4.18 plus 0.14 into 0.396 whole multiplied by 3000 whole divided by 0.47 into 77. So if you calculate this comes out to be 0.911 kilojoule per kg per Kelvin. 0.911 into 10 raised to 3 joule per kg per Kelvin. Joule per kg per Kelvin. That is nothing but 911 joule per kg per Kelvin. This is the specific heat of aluminium. Like this, we can make use of the principle of calorimetry, and we can be able to solve the specific heat. And the principle of calorimetry is heat lost by hot body is equal to heat gained by cold body at steady state. We will continue this in the next video with 2 more concepts, that is latent heat, change of state. That is also very interesting. And afterwards we will be able to solve many number of problems, and that's how we will be able to cover the entire calorimetry. Thank you. Have a nice day. Bye.